Related rates of change. Emphasis here is on the S. It's actually plural, meaning there's going to be more than one rate happening at the same time. It's better to remember this as related instantaneous rates of change. Remember, we usually use the derivative to indicate that instantaneous rate of change. Our objectives today is to use problem-solving skills to find a missing rate of change, or it could just be a missing unknown. We want to reuse Leibniz notation. That's going to be very important, as Leibniz notation often translates to a story or units that will help you tell that story. We're going to need implicit differentiation techniques. We're going to implicit differentiate with respect to time, because in related rates, there are several or more than one function of time. We're going to need to write exact answers, and then as necessary, go ahead and approximate those exact answers. We'll conclude with complete sentences. The general strategy for related rates is to draw a picture or two. If you're going to draw a second picture, I recommend that you draw that picture to indicate a specific moment or specific instance of time. We're going to need to label rates using Leibniz notation. The second step is to actually establish an equation that relates your variables that are in the context of the story. Third, we're going to implicit differentiate with respect to time. You're going to have functions that have the independent variable of t. After implicit differentiation, go ahead and solve for missing instantaneous rate or substitute your values using your mastery of algebra, geometry, and trigonometry. As needed, you could approximate your exact answer with a calculator, specifically a scientific calculator. You should be able to state your answer in a complete sentence. Ask yourself if the answer is reasonable. Should the rate be positive? Should the rate be negative in the scenario? Are your units correct? Make sure you're able to label things in a meticulous manner, especially if you're going into STEM subjects, because those do matter. Your units do matter, and they could often matter in a life or death situation. This strategy may vary slightly due to the complexity of real-life scenarios. Here are just a few examples of relationships. Relationships are usually formulas. Most of these are related to a subject called geometry. Some of them are related to a subject called trigonometry. For instance, you want to be able to draw the relationships as well. So in an oblique triangle with the law of cosines, your angles are usually capital letters or Greek letters. And then the lowercase symbols actually represent the sides of the non-oblique. I should say the sides of the non-right triangle, also known as the oblique triangle. Why don't we illustrate this general problem-solving strategy with an example? Go ahead and read this example many times. You could pause it and read it, 5, 6, 7 times. Don't be surprised in the end that you have read the problem 10 times before you actually solve one of these. I recommend that you use lots of paper and, maybe one full sheet of paper per problem. And if you write big, you're going to need more than one full sheet of paper. I also recommend that you divide your paper in a way where you could actually draw 2 pictures. So I typically draw a moving picture or a picture full of variables, and then I also draw a still picture, or what I call the picture that indicates the moment. So on the left side, I'm going to indicate a picture, and that could be picture number 1, But on the right-hand side of my paper, I'm going to try to indicate a moment or at an instance. And that's when we take a capture, or you take your smartphone and just pull up the camera feature and take a picture of that moment. And then at that moment, we'll try to describe everything that is happening. So let's go ahead and draw a circle. Now, you have to ask yourself, is this radius fixed or is it increasing or decreasing? So you go back and read the problem. If the radius is decreasing, my first picture is actually rather large. So I would try to draw a bigger circle, and then at the moment, I draw a smaller circle. Now just pretend that's a circle. The radius is changing. And we know that the radius is actually decreasing. Now, it also talks about the area of a circle. So can we establish some kind of relationship? And the answer is yes. Area is a function of time, and that is pi times another function of time called the radius. The radius is changing with respect to time. And so that is the relationship there. Now you just got to remember A is a function of time, R is a function of time. As long as you remember that, we could go ahead and remove the T temporarily. It's actually in the background. It's always hidden. Okay, so when we write capital A, we really mean A as a function of time. Now, I'm going to go ahead and implicit differentiate this relationship. So we're going to actually take the derivative with respect to time on both sides of this relationship. Notice that you're going to implicit differentiate. So when you differentiate r squared with respect to time, you're going to need the chain rule. So it's the derivative of the outside function evaluated at the inside function. There it is, times the derivative of the inside function, which is simply dr dt. Now, I'm going to realize that these are the related rates. There's a rate involving area and there's a rate involving radius. Now I go back and read the question again. What is the rate of change of the area at the instance the radius is 10 feet? So this goes on the right-hand side of the page. The instance here is going to equal to 10. We also know dr dt. It's given in the problem. So if you look at this, dr dt is actually negative 2 feet per minute. Now notice this horizontal bar is read as a fraction, and that actually resembles the units of the radius, and this minute here resembles the units of time. So we actually know dr dt is negative 2. Now, can we actually solve for the rate of change of the area? And the answer is yes. All we need to do is actually simplify this expression. We know it's pi times 2 times 10, and then times the derivative of r with respect to t, which is simply negative 2. So dAdt simplifies to be this number here, negative 40 times pi. Now we need to indicate the units. And the best way to indicate the units is try to remember how area units are measured. That would actually have to be square feet. So how do we write square feet? Like that. And then over here, this has to be a unit of time. And in this case, it's square feet per minute. And that horizontal bar is now read as per. Now, how do we summarize this? At the moment, the radius is 10 feet. And decreasing at 2 feet per minute. The area is decreasing (40 pi square feet per minute). And that shows a relationship there. Here's another example. This time the picture is a little bit different. Instead of a circle, we actually have a sphere. And this time the sphere is actually getting bigger. How do you draw a sphere? You could draw a circle, draw an equator, and then that looks like a tiny sphere. Now at the moment, the sphere should be getting bigger. So I'm going to draw a bigger sphere. So remember, I like to draw two pictures. I call it pick one, and then there's a moment picture where you actually take a camera or take a snapshot of what is going on. Now there's a volume. There's actually a rate of volume with respect to time. Now it's asking for what is the rate of change of the radius when the radius is 10 inches. Let's see if we could come up with a relationship. So the volume of a sphere is 4/3 pi, and the radius is changing. So it's a function of time. It's running off a stopwatch. And there is the relationship. Once again, as long as you remember that v is a function of time and r is a function of time, you'll be able to implicit differentiate later. Speaking of later, later is now. Let's implicit differentiate. V is a function of time and r is a function of time, so we're going to need the chain rule. Put the constant out in front, and we're ready to do the chain rule. the derivative of the outside function evaluated at the inside function. That's simply going to be 3r squared times the derivative of the inside function, which is simply dr dt. What is the rate of change of its radius when the radius is 10 inches? So the moment here, r is 10 inches, and we know that dv dt, the volume is changing with respect to time, is given. Now, when I solve for dr dt, I'm going to put this over on the moment side of the page. So dr dt is now equal to dv dt is in the numerator, and we're left with that in the denominator, as long as r, of course, is not 0, and we know it's not 0. We know r is specifically 10 here. Let's simplify. (400) divided by 5 and there you go. There's dr dt. We need to indicate the units. So what are the units here? Well, r is measured in what? R is measured in inches, and the time is measured in minutes. So it's got to be inches per minute. Interpretation, you should be able to summarize this and write a sentence. You may find the approximations at the end of this handout. Remember to use a scientific calculator for your approximations.